So today we are going to talk about BERT. BERT stands for bidirectional BERT stands for bidirectional encoder representation from transformers. Okay. So this is what BERT stands for. Bidirectional, इधर देख लो. Bidirectional encoder representations from transformer, BERT. How do you think in architecture it is going to be different from GPT? So here you explicitly say encoder. Okay. So which means this is encoder only. We have already seen transformers. So BERT was trained only on encoder part. Now, can anybody help me draw that now? So what is the architecture? Quickly now, this is all super easy now. This is multi-head, self-attention. Next will be add and norm. Next will be feed forward neural network. Next will be add and norm. Okay. Now, of course, okay. Now, what else? So you add them, feed it here, and that is what you are going to do it for. So again I am taking this to be 512. What is D model? So D model is 768 for BERT base. So what I am actually drawing here is or maybe I could just do it there. Yes. Sorry? D model is 768. What was D model? Dimensions of these things. Okay. So every branch here, every thread here has a 768 dimensional vector. Now can you help me figure out? So this is one encoder. How many encoders for BERT? Okay. How many multi-head? How many heads? Can you tell me? Easy now. So heads are also 12. So number of layers is 12. Number of heads is equal to 12. D model is 768, which is basically same as 12 into 64. What more? Guys, I don't know ये क्या हो रहा है यहाँ पे. So no, this ये बार बार repeat हो रहा है. So What else is there? So you mean this part? So this what we have kept is 5 and 12. What else? Okay, that is fine. So I think, okay, no. So what is the size of this feed forward neural network? So again, if you see this feed forward neural network looks like 768 3072 and then 768 again, and I don't know that. So check it out whether this uses GALU or ReLU. Should be ReLU, but I am not sure. But it will be some version of ReLU only. Okay. Now quickly tell me, GALU. So here you do GALU. Okay. So here you use GALU. Anything else? So we have done this. We have done add and norm. So by add and norm, now I am not drawing all those skip connections, because with add we understand we are talking about skip connections only. This network is very much similar to GPT, right? This is same as GPT. So then what is the difference? So GPT was just decoder only. This is encoder only. So is there any difference in the number of parameters? I don't know, maybe I should keep this right now. Will there be any difference in the number of parameters? What is it? No, that part I am not yet talking about. Until here. So right now I am not talking about what is the last layer doing. Okay. Last layer we'll talk about, I mean, in a few minutes when we start talking about what is the training task for them. Now we understand what is pre-training and what is fine-tuning. So this is 768. I think I am done with the architecture, unless you have questions. This should be relatively easy. Now, okay, let us talk about the training tasks now. Pre-training. So by the way, just let me cite the paper. The paper title is BERT, Pre-training of Deep Bidirectional Transformers for Language Understanding. Okay. So it is not for language modeling. So if it is not for language modeling, what can I rule out for training task? That it is not predicting the next word in my sequence. Okay. It is not doing that. So the pre-training task for for GPT is the following. So now this, what they call as now, if you talk about this, the authors cite some 1953. So they cite a paper from 1953 where this task was called, closed task. So just to let you know that research paper is basically collection of a lot of ideas taken together, not everything you invent. So this is not a new task that they are training it on. This is known for as long as 1953 at least. I mean, of course, fill in the blanks is a task known since eternity. Yes, the vocabulary of BERT is 30,000, but that's a completely different topic that I'm going to take about separately in the next classes. For the time being, every token to us is a word. Okay, so we'll simplify that, but in the coming classes, we'll actually see the details of the vocabulary for the BERT. So let me just talk about the task first. So mask language model, what they say is, so So this is the first training task we are talking about. Predict a random 15% of the subword tokens. This is how BERT works, but right now we are taking every word as a token. So exact meaning of this we will understand in one of the coming classes. So BERT has, see, one of the big achievements of BERT is it was able to compress so many languages into just one vocabulary size of 30,000. So BERT vocabulary has numbers, it has English alphabets, it has some Unicode characters. So 30,000, not just English words, right? It is able to encode a lot of other things too. Chinese, Hindi, all these words are there because it encodes Unicode as well. So 15% of the subwords tokens. Now replace input word with mask 80% of the time. What does this mean? So we are going to talk about a training task now. What was training task for word2vec? What was the training task for word2vec? So you have this whole unlabeled corpus, and then using that window you make context target pairs and use those pairs as your training data set. Right now, whether you use negative sampling, whether you use the vanilla softmax, the vanilla skip gram model, that's a different thing, but in the end you had a pair. You will, so given a context word, you are supposed to guess the target word, and you have billions of such examples. What was the training task for GPT? Again you have this corpus of unlabeled data. See, this is a common story among all the papers that have led the success of NLP in modern times. you have a lot of, so gone are the days when you had to prepare a data set for named entity recognition, when you had to prepare a data set for sentiment classification. So you train a huge model on some task that may not be so relevant for the test per se, but that gives you a huge understanding of the language itself. What was that task for GPT? For GPT it was next word prediction, basically language modeling. Do you have to do any labeling, any annotations there? No. You have corpus, you fix your context size, and you are going to guess the next word. The moment you are done with the next word, shift your window, and this 512 window you can keep on shifting. Basically you need not shift. What you do is you give batches of various sizes. Now in this case, training objective is this. So this is my first training objective, T1. Predict random, and they correlate MLM. So that's what I have written. Okay, so I'll write training task 1 is masked language model. So what information is this guy giving you now? Should be easy. Right. Okay. So loosely speaking, this is fill in the blanks task.
तो सर ये भी एक तरह से प्रेडिक्शन ही तो कर रहे हैं.
Exactly.
मतलब क्या वो जीपीटी के.
So what is the difference between GPT and BERT then?
जीपीटी में बस ये कर रहे हैं ना कि कॉन्टेक्स्ट में हम लेके नेक्स्ट वर्ड प्रेडिक्ट कर रहे हैं. इसमें पूरा सेंटेंस लेके एक बीच का वर्ड प्रेडिक्ट कर रहे हैं.
So that's a big deal because BERT has access. So BERT in its name has bidirectional encoder. So I'll draw this sometime. When you are, let's say your sentence is, I am going to have a cup of coffee today. Now let's say you mask this word coffee here. So I am going to have a cup of mask today. So the model is supposed to guess what should come here. Now it has information from both the sides, and that is the major difference. That's it. Otherwise, if you see, BERT base is basically same as, if you change this multi-head self-attention to masked multi-head self-attention, then this is same as GPT. Okay. In fact, they define BERT base just to be able to compare with GPT. So this model is exactly same as GPT, except this here you don't have masked multi-head because you are not doing language modeling. Here what you are doing, that is called as masked language modeling. So it was originally called closed task, and now you are calling it masked language modeling. So predict a random, so 15% of your corpus that will be masked, that your language model, that your model is supposed to predict what is the right word there. So up there, the softmax will be done on So I think, can I simply start using a black box now? This is my BERT, yes, this is my BERT. How many inputs do I have? 512. And how many outputs will I have? Of course 512, and each vector is of dimension 768, and this whole BERT is a 12 layer encoder. Okay. So what should be these guys? Let's say this is the token I masked. So this guy here should be able to predict what it should be able to predict? The correct word, okay? And to be able to predict correct word, what am I supposed to do in the last layer now? Something that I had not drawn before. Softmax, right? So that way it is no different from language modeling, because in language modeling you are trying to predict the next word. In this case you are trying to predict the any word somewhere randomly masked, but it is still going to be drawn from the vocabulary size. Note that I am still calling that every token is a word for me right now. We'll fix this later for BERT itself, right? Because BERT is something we are going to use for our programming exercises too. So you are supposed to predict this one. You are supposed to give me word embeddings. I am trying to figure out which word belongs there. Okay, make sense this whole thing? Okay. Now question is predict a random 15% of the tokens. So if you have 1 billion words, you are going to predict how many? 150 million. Okay. Next, replace input word with mask 80% of the time. What do you do remaining 20% of the time? So they do something, so replace input word with a random token What is this? So I am writing this and you should be able to figure out by then. See, so if you have 1 billion total tokens in your training corpus, you will mask 150 million of them. Okay, this comes from here. Now out of those 150 million, 120 million you are going to do this part. 80% of 150 is 120. So for 120 million, you are just going to replace the word with a mask token. Now for remaining 15 million, you are going to do this. Replace input word with a random token 10% of the time. So remaining 15 million, you are going to do this. And for the remaining 15 million, the remaining 10%, leave the input word unchanged 10% of the time, but still predict the word. Okay. See, this is like 10 of you are trying, 3 of you, 4 of you are trying to do something. One comes up with this idea, let us do this. And then you refine this idea by saying, why just stop here? Let's add a couple of these ideas too. If you want to add something more that makes sense, that will also be okay here. So there is, nothing exhaustive here. If you would want to add something more, that is okay too. Okay, so now it says doesn't let the model get complacent and not build strong representation of non-masked words. So no masks are seen at the fine tuning time. Now fine tuning time is something we'll talk about later. Right now we are just talking about the pre-training part. What is fine tuning? Once you have pre-trained on these tasks, so this is task 1, we are going to talk about task 2. What are you going to do in the test time, by the way? This is your training task. What are you going to do in the training time? I mean, this is your training task, and what are you going to do in the test time? What will be your task? I mean, the test task. See, the way we have seen machine learning, you are given a corpus of, or you are given some, total data of size 100. You split that into 80-20. So you train on 80, you test on 20. All these tasks that we are talking about, right? Except the original transformer. What was GPT doing? You use it for language modeling, but you almost never did language modeling in that GPT paper. You used those pre-trained network to do other NLP tasks, which were like question answering. We have seen those things, okay, on which you fine-tuned. Same is going to happen with BERT. Same happened with word-to-vec. You trained it for context target pair, but you never use that thing as training, during test time. So here during test time you are not going to use this. That means during test time you are not going to give it a sentence where something is masked and you are going to predict the correct word. That is not your training, that is not your test task. What is the goal of BERT then? What was the goal of BERT then? See, the idea is, what was the title of the paper? Bidirectional Encoder Representations from Transformer. So you are not being task specific. You are saying, I want to learn representations such that I should be able to do whatever NLP task I want to. BERT was the first paper to do so well on so many benchmarks and outperform all the existing state of the art. So both GPT paper and BERT paper, what information they give us? Once you have a very good understanding, very good representation of the language itself, you don't really need to make a separate architecture for every task, every NLP task that you want to solve. Both these architectures are revolutionary in the sense that they are not the NLP task specific. They allow you to learn aggregate of the knowledge, and then you can fine tune to do that specific thing that you are doing. And this approach works actually better than that individual one, where you make a separate network for every task. Alright, now we are going to talk about the task 2. So, talk about the task 2, which is what is this task? So if you are given this sentence, my dog, so sentence 1 is my dog is cute. Sentence 2 is he likes playing. Okay? The question is, you are given sentence 1, so as simple as this. Given sentence 1 and sentence 2 predict if S2 follows S1. So you are supposed to predict just this. Given two sentences S1 and S2. Here sentence does not mean, you know, that grammatical sentence where it has to start with a capital letter and has to end with a full stop. It can be any arbitrary length part of the corpus. What we care about is, so this is my S1, let us say this is S1, this is S2, both are given. So you start with something called CLS, the exact architecture details I am going to draw in the next class. So SEP is separator, okay. CLS is for the classification token. What you do is, so this first output, okay, this has a special place in BERT, it is called CLS token. When CLS stands for classification, so what we are going to do is, when we will be doing fine tuning for all the classification tasks, we will throw everything else away and we are going to use the CLS. What are the dimensions of CLS? What are the dimensions of CLS? 768. Everything is 768. Okay. So 768 dimensions. What are the dimensions of this SEP separator token? 768. There you don't have to think. Whenever you say token dimensions, that has to be 768. So CLS is 768. Now if you want to do some classification, what are you going to do? Your input layer will have, on top of everything, input layer will have 768. If your output, whichever problem you are talking about, if that has 5 output classes, then 768 and then 5 output layers. Do a softmax, that's it. If you are supposed to predict what is the next token, what do you use here? Softmax again, but this time this softmax will be over the number of tokens in my vocabulary, which for BERT is 30,000. Okay. So we have talked about next sentence prediction. So this is what it is. These two tasks BERT is trained on, and by just doing this it can do wonders. So this BERT paper has been cited more than 110,000 times, I think, right? So before ChatGPT came, this was the hero. But we'll see the GPT family of papers too, because their title reveal you a lot of things. So this, I think, is the right moment to stop and take questions from you, maybe, or maybe no. I can give you some factual details. So this was BERT base. They trained this model to be able to specifically compare it with GPT, because both are exactly same models. The only difference is the masked multi-head attention, yeah, the encoder decoder thing. Now, but they had also trained on BERT large. What are the specifications? So this guy, I am not going to do it for you. You should be able to do it on your own. See, all these things, computing the number of parameters, has been my favorite question since whenever you. So what? So the BERT base, the total number of parameters, so parameters is 110 million. Alright, so BERT large, what are the specifications of BERT large? So BERT large, you have number of layers 24, and what is D model? 1024. So the moment you take D model to be 1024, what is my number of heads? So my number of heads are 16, and that gives me a total number of parameters $340 million. Now, as they say, if you want to train BERT or GPT from scratch, right, that's a very compute, I mean, okay, we can also write a few more things. So if you want to train BERT from scratch on our laptops with a couple of GPUs, that's not going to happen. But if you have the pre-trained BERT model with you, and if you fine tune it on your laptop, that is doable. Okay. So trained on that, remember what did we use for GPT? Books corpus, where they had 800 million words, I think, yes, and English Wikipedia that has somewhere around 'So I think that is it. BERT was pre-trained on a 64 TPU chips for a total of 4 days. What about for GPT 3.5? So GPT 3.5 ChatGPT was trained for 100 days on 25,000 A100 NVIDIA GPUs. Every GPU consumes 6.5 kilowatt. So it is like, you know, more than 1,5 kiloton ACs switched on for 100 days. And this is what they publicly reveal. So how much they have actually cost, nobody knows. Okay. So I think that is it for today. We'll start from the more details of this architecture in the next class. But whatever we have done today is pretty straightforward and simple. So that should not break our continuity when we come back after the small break. Chalo, done for today.